All right, folks. What we're going to do in this video is we're going to walk through a regression screening in Stata, but this time what we're going to do is we're going to work with an interactive model. So before in the previous example, working through screening in a regression model, just having containing first order effects, we'll change things up a little bit differently, basically the same procedure, but a couple of different steps as we're working through a moderation model where we've got some interaction in terms of ordering of looking at some stuff. So for these data, or for this example, we're going to be using this exercise moderation 2 set. And our models that we're going to be running, so we've got 4 different variables here. We've got participant sex, and then we've got NOS, and NOS is going to be giving us an indicator of the extent to which people feel like support resources are useful and helpful. So again, this is going to be negative attitudes towards support utilization. The idea that as scores get higher, these are going to be people who endorse more negative views about whether or not social resources and social networks can be trusted, whether or not they're helpful, so on and so forth. We've got a variable called INQ belonging, and this is going to be a continuous indicator of the extent to which people feel lonely and alienated from other people. And then we've got a social support indicator, 0 to 7, looking at perceived social support with higher scores indicating greater levels of support. And so for this model, our measure of perceived support is going to be our outcome variable. Gender, NOS, and INQ are going to be our predictor variables, but we're also have a couple of moderation hypotheses that we want to screen these data to test out. Our first question is going to involve the extent to which attitudes towards support utilization impact the association between belongingness and support. So here we're going to be looking at an interaction of NOS and belongingness, and seeing the extent to which our attitudes towards support utilization impact the nature of the relation between belongingness and perceived support. And then we're going to ask, does the relation between thwarted belongingness and social support differ across men and women? So here we have a dichotomous sex variable, and we're going to see whether or not this unique association of belonging to support differs across men and women. Okay, so here's our data set, and it looks like we've got 223 people, so a fairly large set here. So what I'm going to do first, as we always do, start by seeing if I have any missing data. Now in Stata, one of the quick ways to do this, if I run a regression model on all the predictors in all the variables in my model, so sex, INQ, NOS, and MSPSS, if I run this, and then remember, if I tell Stata to generate a variable called check and have that variable equal to 1 if the observation was included in this model, right? So if I go through and I do this, what I'm going to see is I'm going to get an indicator variable here that has a value for 1 for all cases that have complete data here, okay? But then what I'm going to do, so if I go through and I sort by that check variable, it's going to do, it's going to take all the cases that I have missing values for, and it's going to put them down here at the bottom. So I can see that I am missing for case 301 and 216, I'm missing an INQ belongingness score. And then for case 189, I'm missing a value for social support. So what I would want to do is I would want to go through and record those, write those down. So 301 and 216, I'm missing an INQ score. For case 189, missing an MSPSS score. So some missing data, but with only 3 cases missing in a sample of 223, I'm not too worried. Okay. Now what I could do is I could just manually delete these, but just because I like to keep track of what I'm doing with my set, if I just hit drop, if my check variable is greater than 1, remember that Stata counts missing values as infinitely large. So if I say drop any cases, if the value for check is greater than 1, those are all going to be greater than 1. So if I go through and I drop that way, next time I open up this data set, if I just use the raw data, I kind of know what I've gone through and done. And so what I'm going to do is I'm going to go through, I'm going to save this as just a scrap working file, because we never want to be working and deleting information from our original data set. So I'll just use this as a different under a different name so I don't lose anything here. Okay, so we've gone through and we've taken a look, found that we've got 3 missing scores, recorded those. What I want to do now is I want to look at my distributions and plausibility of my scores here. So first thing I'm going to do, I know I have a dichotomous variable for sex. What I want to do is I want to take a look at the breakdown of that. So if I go through and I run frequency on sex, I see that I've got about 3/4 of my sample are identifying as female, about a quarter identifying as male. So we've got an uneven split here, but not, it's about a 3-to-1 split. Again, if we go display 166 divided by 54, right? So we got about a 3-to-1 split for women to men on this. Unbalanced, but not something that we would identify this dichotomous variable as too unbalanced to the point where we started to become concerned about things. So we're okay with our categorical variable. What I want to do now is I want to take a look at skew and kurtosis. So here I'm using tab stat with asking for sample size, mean, standard deviation, min, max, skew and kurtosis for my 3 continuous variables here. If I go through and run that, I see what I've got. What I want to do is make sure that my variables make sense given the range of scores that I've got here. So we can see that my NOS variable 0 to 80. So if I look at my min max for NOS, that falls in INQ 1 to 7. I'm good there. MSPSS 0 to 7, so I'm falling in line there. So my variables are looking good in terms of plausibility. So I don't have any scores that are falling out of the real bounds of the scale. Other thing I want to look at here is my skew and my kurtosis values. So if I go across and look at my continuous variables, a little bit of positive skew, that's looking pretty good for my NOS. My MSPSS has some negative skew here. We'll probably notice that in the graph, but again, all within bounds of what we would expect. Looking at kurtosis, remember that Stata gives a neutral kurtosis value of 3. So here, all of these are looking pretty good. Once again, if I use my display command and just calculate sort of that minus 3, so we'd have a kurtosis value of negative 0.53 here. Here, a kurtosis value 0.39, 0.65. So again, we're just subtracting 3 to get sort of what we often see as a neutral kurtosis value of 0. So just making that adjustment. But it looks like, based on these scores, at least from univariate distributions, nothing too concerning that we've got going on here. Okay, but what we always want to do is we want to go through and take a look at graphical graphs of our distributions. So what I've got here is I've set up my graph, histograms for I and Q belonging, and then I'm going to ask for a kernel density line plot here. Notice I've set my bin for 18, and this is just the way I set these. Again, if I take square root of my sample size, which is 220, now that I deleted those 3 cases, and then plus 3, this just is kind of a rule of thumb I use. So I get a bin numbers about 18 bins. So what I've done is just for my histograms used 18 for my bins there. So if I go through and I take a look at my INQ looks like it's got some slight positive skew, but not anything that we're going to be too concerned about, right? And we knew that was going to be positive skew 0.5, but otherwise That's looking okay. Not too concerned about that. Go through, take a look at my NOS variable. That's looking really nice. Again, seeing one case here falling below the lower end of the distribution, but relatively normal distribution here, so I'm okay with that. And then for my MSPSS, my social support, here I'm seeing some negative skew, right? And we knew that was going to happen. Again, we've got a negative skew of close to -1 here. And so it's not problematic in terms of our model, but we're definitely seeing some negative skew here, where the majority of our sample is reporting pretty strong levels of social support. Again, that 7 is the top value here. But then we've got a couple of people hanging out down here reporting some lower levels of support. Okay, so some things to notice about our histograms. Go through and let's go through, take a look at our box plots. For my belonging box plot here, nothing too much. We can still kind of see some positive skew going up. But here's my median, my third quartile, my first quartile. These are actually min-max values here. So INQ is looking okay. If I go through and look at my NOS variable, here we're seeing some values falling above and below 1.5 times the inner quartile range. So here, really nice symmetrical plot with the exception of case 176 falling down below the 1.5 times outside 1.5 times the inner quartile range. Here on the upper end, it's kind of hard to see what's going on. Looks like we have about 4 cases. If we want to clarify this, what we could do is we could go to our thing. We'll go we go gsort. This lets us just put it, we'll just go sort. Sort, this is my NOS variable. I sort that, and so looking at my NOS here, looks like I've got 4 values just above 60 some. And so if I look at NOS, yeah, it looks like it's those 4 values. Where I've got case number, what is that? That's 162, yeah. So these are both values of 63. So 162, 232, 276, and 258. All those values falling above 1.5 times the inner quartile range. So nothing we're probably too concerned about, but definitely want to note those in your screening summaries. Okay. So take a look at that, and then our outcome variable, our MSPSS. Go through here, we're seeing that same evidence of that same negative skew in our median-based statistic plot, and 3 cases here, 291, 333, and 292, all falling below 1.5 times the inner quartile range of our box plot here. Okay, so on our write-up, we want to go through and make sure that we're describing these distributions, just giving a quick description. So overall, in terms of our distributions, some deviations from normality, but probably not anything that's overly concerning in terms of problematic violations at this point. Okay, and especially given the sample size, we've got quite a few people up here. Okay, so what I'm going to do now, I'm going to switch over. I'm going to look for univariate outliers. We'll call these extreme values. I don't like outliers. Okay, and what I'm going to do is I'm going to say just z-score my 3 variables here. And so if I run that, Stata will just go through and calculate z-scores for me, which is very nice. And then what I can do is I can just sum z INQ belonging to z MSPSS. Run those. And here it's giving my standardized scores. So for INQ belongingness, or thwarted belongingness, looks like things are fine. Got a min of negative 0.135, positive of 2.63, but nothing really concerning here. Got a lower value for MSPSS, or excuse me, NOS. This is falling just a little below 3 standard, right? A little beyond 3 standard deviations below the mean. But again, for a sample at 220, I'm not too concerned about that. But here, when we get to our MSPSS, we do see that we've got a standardized score that's pretty low here, okay? We've got something that's 3.59 standard deviations below the mean. That's starting to get a little bit beyond what we can just easily ignore with stuff. And so we probably want to take a look at this. So what I'm going to do is I'm going to sort my ZMSPSS and run that. Okay. And here, if I take a look, see, I've got a couple of scores here, both case number 292 and 333, demonstrating some pretty low scores on our outcome variable. So my observed score for my MSPSS for 292 is a value of 1.33. And if we go back up and take a look at the sample mean for MSPSS, my sample mean is about 5.6. So this is really low. We've got another person who's reporting really low levels of support, a score of 1.58, giving me a z-score of negative 3.38. So probably what I would do, I'm probably not too concerned at this point about these cases, just given the size of the sample and the expectation that we're probably going to have some people who are reporting low levels of support. So I'm not going to be too concerned about these for just yet, but definitely going to want to note these cases as coming up and being flagged as having some low values on my outcome variable here. Okay. So in terms of extreme scores for my continuous variables, belongingness, NOS, looking pretty good. MSPSS, looks like I have flagged a couple of cases here that are demonstrating low levels of support. All right. So what we've done to this point, we've kind of worked through all of our univariate distribution, or our univariate stuff with our typical univariate distributions. What we want to do now is go through and take a look at our bivariate plots just for our baseline variables. And what we're going to be interested here is we're going to be looking for evidence of heteroscedasticity and obvious nonlinearity within my bivariate plots. Okay, so what I'm going to do is I'm going to request a scatter plot matrix with MSPSS, my outcome variable, belonging, NOS, and then I'm going to include participant sex in there. And this is, we can't have a nonlinear relation with a dichotomous variable, but what we can do is we can start to take a look and see if we have weird differences in the distributions of our scores across men and women. Okay, so I'm going to go through and I'm going to run my plot. All right, and so if I take a look here, this plot to me is looking pretty good, right? I'm seeing a nice, what looks like a nice linear relation here. Here for my distribution of my variables across men and women, looks pretty comparable in terms of spread, at least not differences that we're going to be really concerned about here. So that's looking like it's going to be okay. Not seeing any clear nonlinearities in my scores. Everything looks to be all right. In terms of, if we're looking at our scores, nothing that's looking like clear evidence of heteroscedasticity across any of these. Again, if we were to run a regression line or a line of fit through there, this is all looking pretty good. So really, in terms of my bivariate plots, looking for no obvious evidence of nonlinearity. Homoscedasticity of my bivariate plots are looking pretty good. And so overall, I'm pretty pleased with this. So nothing here that's causing me a great deal of concern. So that's good. That's easy. All right. So to this point, what we've gone through, and we've looked at just with our base lower order or our first order predictors of sex, NOS, and INQ, looking at distributions, looking at extreme values, looking at bivariate plots. But our model that we want to run doesn't have just our first order effects. It actually has a couple of these interaction effects, right? So we want an interaction of NOS and belonging, interaction of sex and belonging. And so when we transition into looking at our residual plots and our multivariate outliers and our discrepancies and influences, we want to make sure that we're screening this for the full model that we intend to run, okay? So what I'm going to do is I'm going to go through and create some variables so that I can run my full model. So what I'm going to do in Stata, I'm going to use mcenter command to create centered variables for my 3 predictors. Remember, we don't need to center my outcome variable. That's not necessary. But what I'm going to do, center those, and we'll see in our set, we've now got centered belonging, centered NOS, centered sex. And if I just summarize, just to double check that, I should see mean values of 0 across the board. And that's in fact what we see. This is 2.49 times 10 to the negative 9th, that's functionally 0, right? So zeros across the board, our centering works. Our standard deviations don't change with our centered variables. It just makes the mean value equal to 0 here, okay? So our centering has worked. And so what I'm going to do now is I'm just going to generate 2 interaction terms, one for sex and belonging, one for NOS and belonging, just consistent with the model that we're going to run here, okay? So I'm going to run those, looking at my centered variables. And so now here are my 2 interactions that I'm going to run, okay? Now remember in Stata, well, what we're going to do is we're going to run this model, sort of our model of interest, our main model that we want to run. We're going to run that, but then we're going to ask Stata to save some values. So we're going to ask Stata to save our predicted values, or our y hat. We're going to ask it to save residuals. We're going to ask it to save our studentized deleted residuals, leverage values, and then our influence value is cooks, okay? So I'm going to go through, run this, and what we'll see is Stata has now created values. So this is model implied outcome, my predicted value of y, my raw residual, my studentized, the deleted residual, my leverage, and my influence value here. Okay, so what we're going to start with is we want to go through and start and look at our residuals. And remember that for our regression models, what we need to see in our residual plot is we need to see evidence of linearity, we need to see evidence of normally distributed residuals, and we need to see evidence of homoscedasticity. Okay, so what I'm going to do is I'm going to grab scatter plot, and I'm going to plot my residuals on my y. This is just my raw residuals on my y. Predicted value on the x-axis, and then I'm going to also ask for a lowest fit line here, just so I can go through and see and try and detect any potential nonlinearities. Okay, so we go through and I'm going to run this. And in terms of our residual plot, this isn't looking too bad. Okay, so here is our center line. So we need to be seeing, if we have normally distributed residuals, we should see relatively equal representation above and below this line for any given predicted value of our outcome. And we're seeing that our lowest line is kind of following along. That's looking pretty good. Okay, so I'm not seeing any clear evidence of non-normality in my residuals. I'm not seeing any evidence of nonlinearity in my residuals. The only thing that I start to become a little bit concerned about is it looks like we might see some evidence of heteroscedasticity. Notice that things are looking fine in terms of our spread is pretty even until we start to get here up into the higher end. And now all of a sudden, and this is kind of our most densely packed area of our predicted values, things start to get sort of increasingly small. Now, here at this end, we don't have that much representation, but here if we say this is sort of the spread at this end, and remember we see problems with serious heteroscedasticity are going to be things that are about 3 to 1 difference in terms of the narrowest to the largest. I don't know if we're 3 times, but we're probably pretty close, right? If we take this distance and say, look at this distance here. So it looks like just right here at the end, we may have some evidence of possible heteroscedastic residuals. Probably not anything too serious, but we are seeing kind of a tapering effect as we get higher and higher in terms of predicted values. So probably not anything we need to get too worked up about. But again, something that we'll probably want to go through and take a look at, just because it looks like things are kind of thinning out as we get our errors get less and less in our predictive model, the higher the scores we get. And this is actually probably a function of that negative skew that we're seeing, that we saw before in our outcome variable here. Okay, so something to note, possible stuff with heteroscedasticity. But what we're going to do, we're also going to go back through and take a look at our PP plot and a histogram of our residual values, just to check normality of our residuals as a whole. And so our PP plot here, again, if we're seeing something that's normal, it should follow this diagonal here. And so that's actually looking pretty good. No clear evidence of problematic non-normality within our residuals. If I go down through and I create a histogram of my residuals, go through and run this, again, kind of seeing the same thing here. Everything's, I mean, we got looks like some low residuals down on this end, but for the most part, things are looking pretty normalish. Nothing that we're seeing that's too terribly bad here. Okay, so in terms of our assessment of our residuals for our final model, and this is the model that includes sex, belongingness, NOS, sex by belongingness, and NOS by belongingness, we're seeing that our residuals sort of reasonably normally distributed with our residuals. We're also not seeing any evidence of nonlinearity in my residuals, which is good. The only thing that I might comment on is sort of this decreasing fan shape, looking like maybe an argument for sort of starting to look like some heteroscedastic distribution of my residuals. Again, probably not anything I'm too worried about, but something for our class we might want to notice in terms of describing this plot. Okay, so that takes us through our residual plot with a full model. What I want to do next is I want to go through and I want to take a look at my studentized residuals. Remember that these are my discrepancies, okay? This is deviations in Y space. What I want to look at is, do I have cases that aren't being well accounted for by the model? Basically, is my predicted value way off base from my actual observed value? And what we've stored here is our studentized deleted residuals. Remember that our studentized deleted residual is looking at the predicted value for a case, if that case wasn't in the estimation model, relative to what that case actually showed in terms of the outcome. Okay, so if we go through and we run my studentized deleted residuals, remember the nice thing about our studentized deleted residuals is that they're distributed on a Y, on a Z scale. Well, excuse me, they're distributed on a T distribution, but with 220 observations. That T statistic is going to be asymptotically close to a Z. So we can generally kind of, with a sample of this size, probably just go ahead and interpret these roughly as consistent with Z scores. Okay, and so I see that I've got some high residual, a little over a value of 3, which is high, but it's not too concerning. But this catches my eye. What I've got is a residual, a studentized deleted residual with a value of negative 4.87, right? So roughly a Z-score of 4.87. That's a big deal. That's pretty big, right? So it's looking like I have some cases in my model or some cases in my data that aren't being accounted for well by my model. Okay, I've got a big residual, so I've got a large discrepancy for at least one case in my set. Stata is pretty slick to go through and take a look and find out what those cases are. I can use this extremes command to request, give me extreme values for my studentized residuals, and then also give me the subject number for those. So if I go through and I run that, I see that it's going to give me my 5 largest, or my 5 smallest, and my 5 largest studentized deleted residuals. So here are my 5 largest. Again, my largest is a value of about 3. Not too concerned about that, given our sample size. But here, when I go down through and I take a look, it looks like I got a couple of very negative values here. So case 291 and 364. 364 is kind of borderline, but it's a pretty big gap here. These are 2 cases that are showing large negative residuals, meaning that, remember that our residual is our observed value minus our predicted value. And so if we were negative, it means that we've got a value that was predicted to be quite a bit higher than our actual observed value. Okay, so we've got 291 and 264 that look like they might be problematic, but again, we want to go through and graph these out. So what I'm going to do is I'm going to request a box plot for my studentized residual here. And so again, our large residuals in the positive domain, they're up here, but they're all kind of clustered. We got a cluster of low residuals, but then again, 364 and 291, which were the 2 we saw here, kind of separated out away from the rest of the distribution. If I go through and I run a histogram, again, I'm seeing these 2 cases falling away from the low end of the distribution. And again, these are going to be cases where my observed value was quite a bit lower than my predicted value. And in Stata, we can go through and take a look at this. If I go sort T-res, okay, I go up and I take a look at my studentized residual here, right? We see that my observed score for the MSPSS was 2, super, super low, right? But my predicted value, my y hat, was close to 6, right? So I was way, way off on this case. Also pretty off for this one. Again, I've got an MSPSS score of 3.6. My predicted value was, again, about 6, right? So again, it's giving me these 2 cases, suggesting that these are individuals who my model is not doing a good job predicting. Okay, so in terms of my studentized residuals, probably going to identify these 2 cases as having large discrepancies. Now, this isn't necessarily a bad thing, and it's not necessarily going to be something that ruins my model. We're not going to be perfect in terms of our prediction for all of our cases, but these are scores that are falling noticeably below sort of the ability of the rest of my predicted model. We're going to go through, log these so we can keep an eye on stuff moving forward. Okay. So that's my discrepancies. My discrepancies, got those out of the way, mark my 2 cases here, 291 and 364. What I want to do now is I want to go through and I want to take a look at my leverage values. Remember that my leverages are my measure of multivariate outliers. Okay, remember that leverages are weird cases in X space. So these are going to be cases that have a weird combination of predictor variables. Our discrepancies, that's weirdness in Y space. These are weirdness in X space. Okay. So what I'm going to do, remember that Stata gives us conventional leverage values and sort of rough, just general guidelines for starting to gauge something that we might want to take a look at. If we take 3 times the number of predictors plus 1 and divide that by the sample size, that gives us our a general rough guideline for what we might start to identify as a large leverage value. And again, if I go display 3 times, we got 5 predictors, right? 1, 2, 3, 4, 5. We got 5 predictors plus 1 divided by 220. Get a value of about 0.08. We'll say 0.082 there. Okay. So what we're looking for are values that are going to exceed leverage values that exceed 0.082. Okay. And those are going to get maybe a little bit more scrutiny. So what I'm going to do is I'm going to go through and I'm going to summarize my leverages. And I'm also, because we want to go through, again, remember that our leverages are indicators of multivariate outliers. And we just don't want to identify multivariate outliers and say, oh yeah, it was a multivariate outlier. We want to go through and start to get a sense for why that case might be a multivariate outlier, right? So what I'm going to do is I'm going to ask for descriptives for my leverage, INQ belonging, NOS, and my sex variable. I don't really need that, but we'll go with it anyway. Okay. So this is just kind of a baseline. I look at my leverage values. Again, my threshold is 0.082. My max leverage is 0.129. So I've definitely exceeded in this set. I've got cases that are being registered as potential multivariate outliers. So I want to go through and kind of see where those cases are. Again, what I can do is I can use my extremes command. And again, what this will do is it'll give me my leverage values with my subject number, belongingness, NOS, and sex. And here I'm going to specify, I just want my high values. I don't need low leverage values. I'm not interested in those, just interested in the high ones. So if I go through and I run this, what I'm seeing is I'm getting my 5 largest leverage values, but even my 5th largest one is still quite a bit above the threshold I set, sort of based on recommendations for things to maybe take a look at, right? And if I take a look, I can start to think about why cases might be registering as strange. So it looks like case 233 has my largest leverage value, okay? Value of 0.129. And it looks like I've got, this is a male individual with an NOS score of 48. So its NOS score is about right at the mean of the sample, but I'm seeing a belongingness score of 6.4 when the average for my sample is about 3. So I've got a really, really large, so this is a case with a really large belongingness score. Same thing, if I look at 333, that's the second largest case with the second largest leverage. INQ belonging of 7, so that again, that's a really big score there. I'm also seeing a pretty big score for my NOS, a score of 62 versus 45, right? If I go through and I take a look at 222, again, a large belongingness or large score for thwarted belongingness, indicating someone who's reporting a lot more degree of alienation relative to my sample as a whole. Here we're seeing about average levels of NOS, right? And so we can go down through and take a look. This is someone who's super, super low levels of alienation and super, super low levels of, pretty low levels of unwillingness to utilize support, right? So we can go through and kind of take a look and start to get a sense for what cases what variables might be contributing to these cases being multivariate outliers, okay? But even when I'm requesting just the top 5, the high values on this, it looks like I've still got something that's looking like it's potentially, I don't know what's going on below this, right? So what I want to do is I want to go through and graph these out. Remember that we have rules of thumb, but if I go through and I sort my leverage values, okay, and I go through and I take a look at my leverages, and my cutoff is 0.082 for my leverage, okay, I've got all of these cases, right? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I got 12 cases here that are exceeding my sort of general rough benchmark for what I might identify as a multivariate outlier. Now, I'm not just going to nuke 13 cases out of there and just say they were multivariate outliers, so I got rid of them, right? What we wanted to go through and is take a look and see, are there cases that are really standing apart from the rest. And for that purpose, some graphs can be a nice way to look at this. So I'm going to go through, I'm going to request a box plot. And so again, we see these cases extending beyond 1.5 times the interquartile range, and it kind of continuous goes up. You got 258, but then it looks like we got a collection of scores up here. Looks like 233, looks like probably these 4 highest, all kind of separate away from the upper end of this distribution, right? So yeah, we've got cases about 0.12, and then we've got a gap to 0.01. So I'm guessing that these are going to be these top 4 cases are likely going to be sort of these 4 here. Again, if I go through and I run a histogram on this, same thing. I'm seeing anything above 0.1. Here we've got a case, and then we've got a collection of cases right here. So probably what I'm going to do is I'm going to focus mostly on these cases here. Looking at this top collection, we've got 258 that's kind of eking above a value of 0.1, right? So here's 258, but anything above 258 is just going to be these 4 scores here, 176, 222, 333, and 233. And so again, if we go through, because we've sorted by my leverages, so 158, so yeah, we're seeing these 4 cases here as things that we probably, for this set, we're going to follow up on these. Exploring 13 different multivariate outliers is going to be a little much, but these are 4 cases that we're seeing definitely kind of clustering up and separating from the rest. So what we're going to do, remember that what we want to do is we don't want to just say, oh, hey, these are big values. What we want to do is we want to go through and be able to describe and see within our model, what are the variables that are causing these cases to register as multivariate outliers, to try and understand what's weird going on with this, right? Now we went through and we looked at our primary variables here and kind of got an idea. But remember that for our full model, we also have a couple of interaction terms. And these interaction terms can drive some weird stuff going in our model. So we've got 4 variables, 4 cases that we identified as being potentially problematic. And remember, following recommendations by Tabachnik and Fidel, we can hijack essentially a regression model to start to tell us which of these predictors or what combination of these predictors are driving a case to register with a high leverage value. Okay, so what I'm going to do is I'm going to again sort by leverage. I go through and I say, okay, here's my cases, and these are the 4 cases I'm going to be most interested in. What I'm going to do is I'm going to generate 4 indicator variables, MV1, MV2, MV3, MV4s, and set all of these equal to B0. Okay, so I'm going to go through, going to run this, and what I've got, we can see, is 4 different indicator variables. And remember what I'm going to do now is I'm going to go through and I'm going to take, so for my first case, I'm going to have an indicator variable there, my second highest leverage, third highest leverage, fourth highest leverage, okay? And so what we've got is we've got an indicator variable, MV1 to MV4, that uniquely identifies this case versus this case versus this case versus this case, okay? And what we're going to do is then we're just going to run a series of regression models, not because we are trying to predict anything sort of in like a real life model, and we have our outcome variable as in anything that's interpretable or would make sense. But what we can do is we can use this to trick our regression models into telling us what variables are likely contributing to these cases registering as large multivariate outliers or large leverage values. So what I'm doing is I'm going to regress MV1 onto sex, belonging, NOS, and then my 2 interaction variables. Okay, I go through and I do that, and I see what I can now do is go through and say, okay, what are the variables that are combining to make this kind of a weird case in predictor space? And it looks like for this first case, for case 233, we're seeing that some combination of sex, right? This is male sex. This person's male. Some combination of being male, what looks like a high score on thwarted belongingness, and an interaction of sex by belongingness. My first order effect, my main effect of sex, belongingness, and then the interaction of these two is what some combination is causing this to register as a weird score. So we know that this is a man who is reporting high levels of alienation from friends and family members and other people. The interaction is a little bit difficult to know what's going on, but something about the combination of sex belongingness and the interaction of sex and belongingness is causing this case to be strange. Okay, and so what we would want to do is go through and note that in our data, or in our notes that we're keeping on this. Okay, so we can do the same thing, but this time what we're going to do is we're just going to regress MV2 onto my predictors, and what that's going to do is it's going to go through and give me an assessment for what's causing case 333 to register as a high leverage value. So if I go through and I do that, right, for this case, looks like something strange about it. The interaction of NOS and thwarted belongingness. So we're not seeing any individual case here being strange, but something about that interaction is causing this case here. Right, and we've got a high score for thwarted belongingness. We've got a high score for NOS. Those individually aren't causing any problems, but the interaction here is creating a difficulty. So we'll go through and note that. For our third case, looks like this is a combination of sex, belongingness, NOS maybe a little bit, and then sex by belongingness. All these together creating a problem in terms of making case number 222 sort of a weird variable or a weird observation in X space. And then if we do the same thing for our last one, we see this looks like registering as a multivariate outlier as a consequence of a low NOS score and then an interaction of NOS and belonging here. Okay, so this is 176. So here we have very, very low belongingness score, low NOS score here, but really what's causing this, driving this leverage value is the NOS score and the interaction. Okay, so again, if we go back through, there are several cases here. 258 we could go through and take a look at. So do these other ones, right? We can kind of drive ourselves nuts with this. But what we're going to do is we're just going to focus on this collection and sort of leave it at that, okay? Because again, we had 12 to 13 scores that ended up being flagged as above our threshold for consideration. We're just going to go through and try and take care of and take a look at sort of these biggest ones here, okay? All right. So we've gone through our discrepancies, which is weirdness in Y space. We've looked at our leverages, which is weirdness in X space. What we want to do now is we want to go through and take a look at our cooks, because this is going to be our influence, right? We can have a multivariate outlier, and it doesn't necessarily cause a problem. We can have a large residual or a large discrepancy. It doesn't really cause a problem. But if we start to get combinations of large discrepancies and large residuals, it starts to create a potential to have a large influence or a big impact on results of our model. And our measure that we're going to use here of influence is going to be Cook's. Okay. Remember that for our Cook score, kind of a general rough threshold for, what are we going to say is kind of large? We're going to take 4 divided by the sample size minus the number of people, by the sample size minus the number of predictors minus 1. And if we do this, display 4 divided by 220 minus 5 minus 1. We get a value of 0.019. Okay, and so that's what we're going to be looking at. Okay, so same thing as before. I'm going to take a look at summary of my cooks. You see my max value is 0.107. So yeah, it's a lot higher. So we've got cases in here that are registering as high influence values. If I go through and I request my extremes, ask for cooks and subject, just our high scores, we're seeing this is going to give me my 5 highest scores: 276, 319, 292, 345, and 333. So all of these are sort of high, and still even at the 5th highest one, we're still way above sort of our cut point here. If I sort my cooks and I go through and take a look, I say, yowza, my cut of 0.019. So again, all of these cases are technically going to register as high influence values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13 cases being registered. And so again, we're not just going to go through and indiscriminately throw out 13 cases and say, oh, these were high influence values and be done with it. We're going to lose a lot of our sample that way, right? And we also want to be very thoughtful about not throwing people out just because they're not doing what we want them to do, okay? But what we want to do with this many cases, again, is go through and plot this to see if we can see which cases are really causing some problems with things. So if I go through, and this time in Stata would do cool drop line plots. And so what I'm going to do is I'm going to, again, sort by cooks, and then I'm create a drop line plot for cooks with a label of subject here. Go through and do this, and this is kind of clutch. What I can see is really I've got this collection of actually the 5 scores that came up as our stream are the 5 largest scores are really sort of separated from the rest. Now, if we were to get rid of these, now we've got a new set of scores, but for our full set, it's going to be these scores that are going to have, or these cases that are going to have the highest Cook's D, and these are really, really high influence values here, okay? So what we're going to go through is we go through, record the case numbers, the value for the Cook's D, and identify these as our most problematic in terms of influence, and again, being really distinct from the rest of stuff. Okay. So at this point, we've gone through and we've talked about a lot of, like, so we got our leverages, we've got our influence, we've got our influence. And so, but looking at these individuals is, again, it's nice sometimes to go through and be able to kind of plot some of these together. And some of these combination plots can be a nice way to try and say, okay, so we've seen different cases come up. How do I maybe consolidate this? Are there a set that I should be really concerned about? And again, these combination plots, this leverage by squared residual plot that Stata provides is really nice in this respect. Okay, so what we're going to do here is we're going to plot our squared residuals on the x-axis and our leverages on the y. And if I go, dang it, all right, this is gonna, for some reason, Stata will do this if I've gone through, and so I'm going to go through and I'm going to just do it down here. So I'm going to drop, so I'm just going to recalculate all my diagnostic stuff. So I'm just going to drop my predicted values down through the multivariate outlier stuff because I've already got those. So I'm going to go through, get rid of those. So you may find that Stata will do this. So we just got rid of those. And then if we go back up to and rerun this, so we're just recreating stuff that we had already gone through. But before we start fooling around and sorting things, let's go down now and just run our leverage by residual plot here. There we go. That's looking good. Okay. So what we've got is a normalized squared. So basically our squared residual value. So this is going to be our discrepancy. And then we've got a leverage value. This is going to be our sort of leverage or our multivariate outlier. What we're looking for in terms of cases that we're really going to be concerned about is stuff that's going to be up here in this corner, right? Now we've got something that's a huge residual here, case 291, we've already identified that. We've got cases that are high leverage values, but really what we're looking at is stuff that's hanging out up here, a combination of high leverages and high residuals. We're not really seeing anything up here. So in this case, the plot is nice, right? And these red lines are average levels of leverage, average levels of my normalized squared residual here, but we're not seeing anything up here. So this plot isn't necessarily giving us anything additional. Other combination plot we can look at is this influence plot, right? And what this one is going to do, remember, is it's going to give us a scatter plot, and we're going to kind of flip this around, plot our studentized residuals on the y-axis and our leverage on the x-axis. But what we're going to do is we're going to, for our individual points, we're going to weight the size of that by our cooks, our influence value, okay? So if we go through and we run this plot, this is pretty slick, okay? Again, what I'm looking for in this plot are things that are happening sort of way up here and way down here. So this is going to be cases with high leverage values and very large magnitude, either in positive or negative direction, studentized residuals. And the size of these of our points here are weighted based on this on the influence point. So we can see 276 and 319. These both have large influence values in terms of Cook's D, but they're not hanging up out here where we would normally start to see or start to be concerned with individual stuff. And so really, I don't know if this plot here, at least for these data, is giving us much more of sort of an idea of what cases might be sort of the most important to go through and take a look at, or having the sort of the largest potential impact on our outcomes. Okay, so I'm going to sort of close that down and sort of close this. So one of the things, we just got a lot of information, and one of the things that I've started to do to help me kind of organize and say, okay, so I've gone through and I've looked at residuals, I've looked at leverages, I've looked at influence, I've looked at combination plots. What does this tell me in terms of how do I put this together to try and sort of make sense for what I should be looking at in terms of cases, right? What I started to do is go through and take a look and start to plot this out here, right? Just to kind of keep track of stuff. So I've got two cases that ended up having univariate outliers on my outcome. So these were my cases, 292 and 333, that had really low, people reporting really low levels of support. Then I had a couple of cases that identified as having really large residuals in the negative direction. Again, these are cases where my predicted value was a lot higher than my observed value. And so 291 and 264 came up as high discrepancy values. Then I transitioned in my leverages, and I had 4 cases that I flagged here, 333, 233, 222, and 176. And again, what I've done is I've recorded leverage values and then the individual predictors that were causing these to come up as hot, right? And then I've got my influence values. Again, I had 5 cases here that ended up being problematic. So I've got my Cook's values here. And then for my leverage by residual plots and my influence plots, nothing much came up there. But if I'm going through and trying to decide which of these cases might I want to explore further, doing a more fine-grained assessment of the extent to which these cases are impacting my outcome, I might go through and take a look at 333 as a possibility, as a sort of something that might require additional scrutiny. Here we've got a univariate outlier, something that's coming up as a multivariate outlier, and one of the highest influence points within our set. So I might take a look at that. And then again, I might take a look at 276 perhaps. 276 this is just the highest, my highest Cook's D. And remember when I ran my plot here, like this was really high. This was exceptionally high in terms of my Cooks. And so maybe that one as well. Now I could go through, depending on how much I want to fool around with my data, I mean, I could go through and take a look at some others, right? But again, we want to always have good justifications for why we're excluding data because of screening, because we had lots of stuff come up in terms of leverage and influence, and that's generally how behavioral science data will go. But this one is coming up hot on a couple of different things. This one is just a really large influence value. So I might go through, and so my concern is if I were to have a model and finding certain evidence for certain effects, but all that evidence is predicated on one case or one or two cases, I start to become very concerned on whether or not that's a real effect, or whether or not it's just something having to do with strange values in my outcome. Okay, and so these might be the two that I would suggest maybe for continued looking. So maybe run the model with and without these cases, and see how much of a change in our coefficients we get. Sort of these other ones here, those also aren't sort of maybe good, and sort of these ones. But again, sort of we want to get that balance between just scrapping everything that doesn't immediately fit versus doing a good job of making sure we don't have cases in our set that are completely sort of one or two that's just driving all of our effects that we're seeing in our model. Okay. So that goes through, takes care of our residuals and our leverages and our discrepancies, our influence. Last thing what we want to do is we want to go through and take a look at our collinearity stuff, right? We haven't done that yet. So what I'm going to do in Stata is just I'm going to get pairwise correlations between, I don't need to worry about my interaction terms here. So just my bivariate correlations between my predictor variables. And what I'm seeing here, some strong variables, my output, my outcome variable, my MSPSS, showing strong correlations with I and Q belonging and NOS total, which isn't too bad, right? I'm fine with that. I would hope that my predictors hold a relationship with my outcome. But here, we're seeing a pretty strong correlation, 0.66 between belongingness and NOS. That's high. Not maybe to the point where we're concerned about sort of our model falling apart, but it is pretty strong, right? So we would just want to make sure that theoretically that these are sort of reasonably distinct variables to have in our model. So everything looks within bounds, but just definitely want to take a look at, or sort of note that we do have really high, strong correlation between NOS and our belongingness variable. So this does a nice job of getting at bivariate correlations, but what we can have in our regression model is sometimes we have sort of weird combinations in multivariate space that come up. So what I'm going to do is I'm going to regress, sort of run my main model here, okay? And then what I'm going to do is I'm going to ask for my VIF. This is going to give me my VIF and my tolerance statistics, okay? Remember that what we're looking for in terms of sort of conventional benchmarks for problematic multicollinearity is VIFs in excess of 10, or tolerance, which is 1 divided by VIF of 0.10 or less. None of our variables here are registering this. We've got some tolerance levels that are lower for belongingness and NOS, but that makes sense given that we just saw that those two things are pretty highly correlated. But nothing here is looking like we've got evidence of problematic multicollinearity. Okay, if we did find something, remember we can request call diag2, go through and give us some additional diagnostics, but for this we're fine because everything's looking okay. All right, so that takes us through all of the screening in terms of going through and keeping track of what we've done in terms of our write-up. Okay, Again, following the framework that we've used in class. Here we've got our accuracy, plausibility, sort of noting our 3 missing values, our final set that we're going to be using. Here we're looking at our univariate distributions and our histograms, box plots for each given a description, kind of identifying what's going on here. Here, our ratio of our breakdown or our split of our dichotomous variable. We often forget that, but again, it's unbalanced, but sort of reasonable for the types of analyses that we're running. Here we're looking at our extreme values for nothing much for INQ or NOS, finding some stuff for the MSPSS, so sort of taking a note there. Our bivariate associations, looking at linearity, homoscedasticity, residual distributions, taking a look at that, then transitioning into our leverage, our discrepancy, leverage, and influence. So again, a couple of high leverage values here, or excuse me, high studentized residuals. Here we've got, this was actually 12 cases. 12 cases registering as high leverage values, 3 times the expected average here. These were our 4 cases. 233, 333, 222, and 176 that we identified. These are the variables that came up as sort of contributing to these cases being high leverages. Here we're going to go down through, take a look at our influence, talk about our Cook's D, identifying cases there, and then talking about our plots, failing to identify anything sort of coming up high, combination of high leverages and studentized residuals, but just noting that there. And then down here, taking stock of our multicollinearity. Okay. So in terms of stuff that came up, cases with missing values, we have a couple of large residuals, some possible heteroscedasticity in terms of our residual plot, and then cases with discrepancy, leverage, and influence coming up. Okay, so for these data, kind of bring it all home. Missingness, not too concerned about that. Evidence of heteroscedastic residuals, it was just limited to the top end, and it was pretty, just that sort of very high end is maybe sort of questionable. We might want to take a look at it, sort of particularly that specific pattern where we have decreasing variability in my residuals with increasing predicted values. Generally, we often associate that with inflated standard errors. If my standard errors are too big, then my tests and my predictors are too small, and so I can sort of run the risk of overly conservative tests. Probably not super concerned about this here, but it would be consistent with if we did have sort of maybe stronger evidence of heteroscedastic residuals. We also saw cases with large residuals, high leverages, high influence. We're identifying 333 and 276 as maybe the highest levels of scrutiny here, and sort of wanting to go through, explore these, maybe look at our model with and without these cases just to make sure that we don't have any measures that are, or any effects that are being largely driven. It looks like we have evidence for an effect, but in fact, it's just due to sort of maybe 1 or 2 weird scores. Okay, so that takes us through sort of the full screening here. The only other thing that we can do in Stata in terms of our follow-up analyses is we can go through and run. So we had talked about maybe running a model with and without a couple of predictors, or excuse me, a couple of different cases. Stata makes this easy. What I can say here for some follow-up analyses, I'm going to say I'm going to screen, and I've identified 333 and 276 as my 2 cases that maybe I want to look at without, right? So what I can do is I can tell Stata to quietly regress MSPSS onto sort of my predictors here, right? And I'm going to store these estimates in the program under the label base, right? Quietly just means it's going to run it without throwing up all my output. It's just going to run it within the model, and then it's going to store those results under the label base. Then I'm going to do the same thing. I'm going to run this quietly, but I'm going to regress, and I'm going to run the same model, but this time I'm going to run it if I'm not including variables subject 333, right? So I'm going to run the whole model, but I'm just going to exclude participant number 333. And then I'm going to store results in that model as x333, okay? And then I'm going to run another one. I'm going to quietly regress my model if not in subject 1. That should be 276. I'll change that, right? And save that as 276. And then maybe I'm going to run a separate model excluding both of these cases, okay? So what this is going to do is it's going to run my regression models, and it's going to store the results in a couple of different, under a couple of different labels. And then what I can do is I can run a table that puts together my base model with everybody, my model without 333, my model without 276, and then my model without both of these folks, right? And then I'm just going to get rid of the constant. This is setting decimals, asterisk for effects meeting conventional benchmarks for interpretability. Okay, so I'm going to go through and I'm going to run this, and we'll see what happens. So Stata just ran my regression model without sort of giving me, it just did it quietly and stored the results here, 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 and here. And what I can look at, if I go down through and I take a look at my results, here's my base model, okay? And what I'm seeing is I get an interactive effect, or so at least something that's p less than 0.05. I'm seeing something get starred for this interaction plus NOS and belongingness. But if I get rid of case 333, this interaction disappears, okay? But then if I get rid of, instead of 333, if I get 276, that interaction looks like the coefficient gets stronger. But then if I get rid of both, now it's gone again, right? And so what we've got here is it looks like we have an interaction term that's completely dependent on having a couple of variables in the model, right? And so if I go down through and I take a look here and I regress my model, my full model, right? And I'm looking at this NOS by belongingness interaction, right? Seeing that it's right there at 0.05, right? Which is weak evidence for anything anyway. I wouldn't bet anything that this is going to go through and replicate in a separate sample, right? Well, I guess it's a coin flip. It's a 50-50 call, right? But if I go through and I run the same model, this time not quietly, just give me my output, but I exclude participant number 333, we see that my interaction that was p equal 0.05 is now 0.151, right? So the removal, in a sample of 220 people, the removal of one individual completely wipes this out. That's a problem. That's what the type of thing that I'm not comfortable reporting, publishing, if it's sort of just breaking down to one, if this entire moderation effect depends on whether or not I have case 333 in the sample, I'm concerned about that, right? By contrast, if I just run the model without case number 176, it still shifts, but not a whole lot. If I look at it without both of those individuals, now it's really not anywhere. So basically what it's looking like, just based on the two cases that I identified as maybe the most problematic, right? 333 and 276 having a big impact on these effects that are coming up as interpretable based on a threshold of 0.05. If that's the case, I'm very concerned about the stability of that effect. And so that might be strong evidence for getting rid of those cases, saying that sort of had an impact on the stability of effects moving forward with stuff. So, but that kind of takes us through some stuff through the screening you can run in Stata. Hope this was helpful. Let me know if you run into problems. Otherwise, good luck with these moderation analyses.